the video. Alright, so we're going to look at K-maps, and K-maps are a way to verify that you have in fact written the minimum product of sums or sum of products form of the circuit that you're trying to look at. Okay, so the idea with a K-map is that it's set up so that all of the squares share at least one variable with their neighbor. So if you have an x1 in one square, then the neighbor might have x1. Or if you have x1 bar, the neighbor might have x1 bar. And if you look at the way it's set up here, this 0, 0, that corresponds to x1 bar, x2 bar, where they're both 0. 0, 1 corresponds to x1 bar and x2, with x2 not being complemented. And then the third one, 1, 1, is going to be x1, x2. Notice these don't go in numerical order, 0, 0, 0, 1, 1, 1, 1, 0. The reason it doesn't go in the order 0, 0, 0, 1, 1, 0, 1, 1, which would be the binary numbers of 0, 1, 2, and 3, is because these two don't share any variables in common. For the first one, it has x1 equal to 0 and x2 equal to 1, and the next one has x1 equal to 1 and x2 equal to 0, so they don't share anything in common. But if we swap these two, 0, 0, 0, 1, 1, 0, 1, 1, 1, 1, 0, now the first two share the 0, x1, 0, the second and third share x0 equal to 1, and third and fourth share x1 equal to 1. So always be careful with that. And then the last column represents x1 not complemented and x2 complemented. And then over on the side, this gives me x3 complemented and x3 not complemented. Now we're looking for groups that we can circle that have ones in them. And we need to cover all of the ones. And we want to try to do it with as big circles as possible and as few circles as possible. And our circles can only contain a power of 2 number of ones. They can contain 1 1, 2 ones, 4 ones, 8 ones, or 16 ones, but not 3. So for instance, I could not do that. That doesn't count. It has to be 2, 4, or a power of 2. It has to be the circle. And you probably remember from class that the way the K-map is set up, they can wrap around as well. So for instance, on this first K-map here, I can get this group right there, and that covers both of those ones. So that would be an efficient way to do it. So that gets both of those ones, and then to get the top 2 ones, I can get that. So that is 2 circles of size 2. Can I do any better than that? I don't think so, because I can't get a group of size 4, and I can't get less than 2 circles. So sometimes there's more than one right way to do it, but this way is going to be as efficient as any. You might ask, why do I want to do this wrapping around thing? And the reason why is the bigger my group, the smaller the number of variables I'll use, which means the simpler the function. So how I name this now is I look at this group and I look at what variables it represents. So it represents, this top group right here represents these two that I just underlined and this one right here. And so I want to look for the things they have in common. So the way I name this is for the things they have in common. If it has both versions of a variable, it's not going to be in my name. So this group right here, both of these squares have x1 not complemented. They have x2 complemented and x2 not complemented, so we don't use x2. But for both of those squares, x3 is complemented, so we have x3 bar. So when we circle the ones, we're doing a sum of products, and the things that we circle is going to be a product, and then our next circle, that's going to be a sum. And then this bottom one that wrapped around, that one, they both have, let's see, I'm looking at this column and this row. So I want to look for the variables that are in common for those. So not x1, that has x1 bar and x1 not bar, so I would not include that. It has x2 bar, so that gets included. And it has x3 not complemented. So that is going to be our Carnot map for that one. So for this next one, the way I usually do these is I start by looking for the biggest group I can possibly find. So I have 8 squares, so I could look for a group of 8, which I don't have. Do I have a group of 4? And the answer is yes, I do have a group of 4, so I'll get that. And then I still have 1 left to get. And so I could just circle it all by itself, but that's not the best answer. The best answer is to get this group right here. And the reason why is if I got this one all by itself, that would correspond to x1 equaling 1, and x2 being complemented, and x3 being not complemented. That would correspond to x1, x2 bar, x3. That's if it was all by itself. But if I do the column right here, then that means that I don't include the x3 because the column includes x3 and x3 bar. So by itself, it's just x1 and x2 bar, and then this top row. Rows and columns are really easy. You just have to look either to the side or to the top to see what it is. And for this one, I'll look over to the side and I see that that's x3 bar. And please stop me if you have any questions. Okay, so those were some 3-variable Carnot maps. Now we'll look at some 4-variable Carnot maps. And let's see, so I see that I can do this with a group of 4 and a group of 2. Is that what you got? Okay, so my group of 4 is, and the other thing to be aware of is not only can you wrap around, you can also do the 4 corners or 2 corners, or you can wrap around, like if I had one that looked like this. So if I had one that looked like this, I could catch this one with this one, so I can wrap around that way. And the one that I just did over here for fun, it looks like I would do that, and that, and that. I think that's probably the best way. You can also do, if I had 2 bottom corners, I could wrap around to do the 2 bottom corners. If I had 2 top corners and not the 2 bottom corners, I could wrap around and do those. I can't wrap around diagonally. I can't get the top right and bottom left. Okay, so on this one, I saw those 4 and this one, and the 4. Now with a 4-variable Carnot map, the number of variables you'll have in your expression, well, with any size of Carnot map, the number of variables you have in your expression is related to the size of your circle. So if you just have one thing in your circle, then you will have all 4 variables, either complemented or non-complemented. If it's a group of 2, you'll have 3 variables. If you have a group of 4, you'll have 2 variables. And if you have a group of 8, you'll have 1 variable. That's for a 4-variable Carnot map. If you had a 3-variable Carnot map, a group of 1 would have 3 variables. A group of 2 would have 2 variables. And a group of 4 would have 1 variable. Yeah, just like we had up on that one. Okay, so this group of 4 on the 4-variable Carnot map, I know is going to have 2 variables, so let's see which 2 they are. It'll be the 2 that they have in common. So they're in this column, and these rows. And so what they have in common is this 0 and the first 1. So that 0 is x2 bar, and the 1 is x3. So when it's 0, it's complemented, it has the bar, and when it's 1, it is not complemented. And then this group right here, so that group has these 2 columns and this row, and so what they have in common is they all have the 0 and 1 for the x3, x4, and they also have x1 equal to 1. So this is plus x1, x3 bar, x4. Is that what you got? Okay. And then on the next one, I feel lucky because I see a group of 8. So I will grab that group. And I have 2 left. And a lot of times people ask me, and what I'll do with those 2 is I'll grab a group of 4. And a lot of times people ask me, why don't you just grab the 2? And the reason you don't grab the 2 is the bigger the circle, the fewer variables you'll have, the simpler your expression will be. So if you can make it bigger, do. Even though you think, well, I don't need to, I've already got those ones. But we'll see the difference in a minute. So when I get this big circle right here on the bottom 2 rows, what they have in common is only x3 equal to 1. So that's x3. Because in those 8 squares, x4 is both 1 and 0, x1 is both 1 and 0, and x2 is both 1 and 0. So that big group right there is just x3. On this circle right there, that involves these 2 columns and these 2 rows, and what they have in common is x1 is 1, so not complemented, and x4 is 1, so I'll have x4. And so that's the simplest one. If I had just done, that's our answer. If I had just done these 2, then those 2 would have been, let's see what it would have been. So what they have in common is x1, not x2, x3 bar, x4. So that's what I would have gotten if I had chosen those 2. So let's look at that. So if I had chosen that, I would have x3 and x1, x3 bar, x4. So let's look at this algebraically. x3 plus x3 bar, x1, x4. That's like if I had x plus x bar y. That's equivalent to x plus y. So if I have a variable by itself plus the complement of that variable times something else, the complement of that variable can go away, and that's exactly what happened here between those 2. Okay, so on this next one, this next one has, it's a little bit tricky. So this next one, I see two groups of 4 and a group of 2. Yep, that's what I see. So I always look for the 4 corners because I feel like there's going to be one on the test and I'm going to miss it because about every other year there's a group of 4 on the test and people miss it. So there's that group of 4, and then there's this group of 4, and then I have this 1 left over, and the biggest group I can get to hold that one is that group right there. So remember, a group of 4 should end up having 2 variables in it, and so the 4 corners. So the 4 corners involve those 2 columns and those 2 rows. So what they have in common is x2 bar and x4 bar. Now this bottom group of 4 in the bottom left corner, what those have in common are these 2 rows and these 2 columns, and that gets me x1 bar plus, that's from the top, and then the rows give me x3. Oh, x1 bar, x3, and then this group of 2 has x2, x3, x4. Okay. All right, now this next one, I see 3 groups of 4. And I see 2 ways to do it. Do I see any better way? I don't see any way to do it with less than 3 groups. So the 2 ways I see to do it are like this, like this. So with those, so that's one way. And then another way would be to get those, and those. And those are both correct. There's not that there's one right one and one wrong one. Those both will be equally simple. I like this one right here because I find rows and columns particularly easy to write because it's really easy to see what they all have in common. So for this first one, this vertical row there, that is x1, x2. And then the circle in the top left is x1 bar, x3 bar, and the circle in the bottom right is x1 and x3. Now if I were to do it this way over here, this circle is the same. These 2 are the same, and that one was x1 bar, x3 bar, and the bottom right one was x1, x3, and then this one in the top middle is going to be x2, x3 bar. So any questions on that before we get to our 5-variable Carnot map? Okay, so I want to warn you about 5-variable Carnot maps because there are different ways of doing them, and the different professors here that teach digital logic use different techniques. They end up with the same result, but if you end up having a different professor for Digital Logic 2 than Digital Logic 1, they might use a different technique. So if I recall correctly, the way Dr. Trahan does it is you imagine the 2 Carnot maps on top of each other. And then in your 5th variable here, x5, is what is on the two different Carnot maps. The way the other professor does it is with a mirror image. So I'm going to do this one first, the way that y'all are doing in your class, and then I'm going to do one the other way. And if you're not interested in learning the other way, you can just, fast forward to the next thing. So what I want to do is I want to find the groups like I would find them on each individual Carnot map, but then I also want to imagine that these are stacked on top of each other, and if they line up when stacked on top of each other, that I can connect those as well. So on this particular one, this group right here and this group right here, if they were stacked on top of each other, those would be connected. This group and this group, if they were stacked on top of each other, they would be connected. And then I have one all by itself. So now to name this, let's look at what they have in common. If they are connected across the two Carnot maps, they don't have an X5, because the X5 is different. It's 0 on one of them and 1 on the other. So it's not going to be, if they're connected, it's not going to have the X5. So what they have in common is this row, this column, and those two rows. So that gives me an X1 bar and an X3. Plus, oh, and I made a mistake, and we'll come back to my mistake in a minute. And then these two, what they have in common are X1 and X3 bar and X4. And then my mistake was, do you know what my mistake was?
Can you just leave that by itself? The top right corner?
I mean, I can, but it'd be not minimum. You're saying that I shouldn't leave it by itself.
Sure.
Yes, right. I can make a bigger circle. And so for some reason my head had it that, oh, you can't do that. It's like, of course I can do that. There's nothing wrong with that. So what they have in common is they are not connected. So that means X5 equals 1. And they also have this column and this row. And so that gives me X3, X4 bar. Well, I'm sorry. X1, X2 bar from the top, X3 bar from the side, and X5.
Oh, yeah, I forgot about the X5.
Ah, don't forget about the X5. Okay, all right. Okay, so if you are interested, here's the other way of doing it. So what you do, and I hope I can remember because it's been several years since I have done this, is you draw them side by side, so stuck together like that. And the one on the left, you just set up normally 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0. And the rows on the second one are going to be the same. 0, 0, 0, 1, 1, 1, 1, 0. But the top is going to be the mirror image of the first one. So it's going to be 0, no, not. It's going to be 1, 0, 1, 1, 0, 1, 0, 0. So now let's see how, because sometimes you'll have to fill in a K-map. Let's see how this second one's going to be filled in. So this group down here, it has these ones are in the column that has 0, 0, and the rows that have 1, 1, 1, 0. So those ones would go there. These ones would go here. These ones would go here. And this one would go here. And now I treat this like one big Carnot map. And so this bottom group can wrap around. This middle group is a group of 4. And then I have that group of 2. And if we look to see what those are, it gets us the same answer as we had over here. So that's just another way of doing it. I like the top way because that's the way I learned it first. Okay, so now we need to find the minimum product of sums for the function that has min terms 1, 2, 3, 5 using a Carnot map. So product of sums. Everything we've done so far has been sum of products. Have y'all done Carnot maps with products of sums yet? Okay, so I'm going to stop this. Have y'all done 5 variable Carnot maps?
We haven't gone beyond 2, I mean beyond 3.
Oh, okay, I might split this up. Okay.